No one wants to manage databases if they can avoid it. That's why MongoDB made MongoDB Atlas, a global cloud database service that runs on AWS, GCP, and Azure. You can deploy a fully managed MongoDB database in minutes with just a few clicks or a few API calls. MongoDB Atlas automates deployment, automates updates, handles scaling, and more so that you can focus on your application instead of taking care of your database. You can get started free at mongodb.com/atlas. Now, if you're already managing a MongoDB deployment, Atlas has a live migration service, so you can migrate it easily with minimal downtime and then get back to what matters. Stop managing your database and start using MongoDB Atlas. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Guy Godin. He is the author of VR Desktop, Virtual Desktop at vrdesktop.net. How are you?
I'm very good, thank you. How are you, Scott?
I am really excited to talk to you because, we all use applications that enhance our lives. They might be utilities or things that make us happy. Maybe we live in them because we are using them like Outlook or Visual Studio. Maybe they're games. But virtual desktop, which is a term that people think about when they remote into a computer, is an application that I think has really enhanced my virtual reality experience. Maybe you could tell us what it does.
Sure. So Virtual Desktop is an application that I developed originally for the Oculus Rift and HTC Vive in 2014. At the time it was the Oculus DK1 and Oculus Development Kit 2. And so I started working on this app that lets you use your computer while in VR. It might sound strange. Why isn't that something that you can do already? Well, it's mostly because VR headsets are connected to your computer via an HDMI cable and a USB cable. But they only letted you run games. And then when you finished your game, you took the headset off and then you start another one, you put the headset back on, right? It was very, very crude user experience. So what I decided to work on is an app that lets you use your computer and stay in VR the whole time. So you can launch a game, then go back to the desktop, then do something else, and maybe launch another game later on.
When I plug in a headset to a computer, whether it be a desktop or a laptop or whatever, is it another monitor? Does it show up as an extended monitor?
Well, initially it did. It acted as a monitor in Windows, and you could see it in the Windows display settings. But Oculus used what they call a direct mode, where they no longer are detected as a monitor, and now they're detected as a peripheral. So initially it did, but nowadays it doesn't anymore.
Okay. So I'm hearing you say that in the early days of VR, that was a thing. You'd have 1, 2, 3, and then a fourth monitor would appear. Yes. But now it is a separate thing. But it does happen over HDMI, and then virtually we'll talk about in a minute.
Yeah. So the first versions were all wired, were PC VR headsets, but since a few years ago now we have mobile headsets which run on Android and are powered by Snapdragon processors, the same thing you have in your phone. So basically they're wireless as device. So I did a version of my app which is a mobile, which lets you stream your desktop over Wi-Fi to your headset as if it were connected.
Okay. So we're going to have to parse this apart and take this apart a little bit at a time. Let's start with tethered first and move our way over there. So when I started thinking about virtual reality, I would have a super powerful computer with a super powerful video card, and then I would tether with a long cord this I thought of the VR headset as a separate screen that was kind of attached to my head, and all of the stuff is happening over that wire. But you don't see, like you said, you don't see Windows Explorer when you plug in your headset. You see their virtual world.
Right, exactly. So because you can't just pipe a monitor directly onto the headset, because the screen is basically an inch from your eyes. So if you actually put the output of a monitor directly there, it would be as if you were standing an inch from your monitor. You wouldn't be able to see anything, right? And there's also stereoscopy, where you have two images which are almost the same but slightly offset. And that's how you get stereoscopic vision, like in 3D movies, for example. So
how you get that sense of depth.
Right, exactly. So it's one way to show depth to the user is to use that difference in between the left and the right eye. There are
Hmm.
other cues like moving your head left and right, or and these will give you other cues. So there's a bunch of different cues that you can use, but stereoscopy is the main one.
So if I were going to see my desktop on a virtual screen, is it a big flat square? Is it like a projector that I'm in an office building and there's a projector up on the wall and it's just a flat square floating in front of me?
You have the choice. You can, by default, it's a curved screen and you're in kind of in a space environment. So it's like a nebula, and then you have the virtual screen in front of you, and then you can resize it. You can change the curve of it, but you can also, like in my app, I have custom environments. So you can be like in a movie theater and have it simply displayed on the theater screen. So it's good for watching movies or be really immersed into whatever you're watching.
Wow. Okay. So, what is the architecture of this? Are you doing screenshotting? How are you streaming what's on the computer screen, the computer desktop, into this game environment and doing it with low latency?
So when I started the app in 2014, there wasn't really good ways to capture the desktop in Windows. Windows had like a way with GDI to do it, but it was really slow and it tanked your computer basically. But with Windows 8.1, Microsoft released the desktop duplication API, which is a way to essentially do screen sharing. So I used that API to essentially copy the desktop image on the GPU and then render it in VR so that it's very low latency that way. So it's just a memory copy essentially on the GPU.
So it's a memory copy. So I'm going to be very simplistic and then you can correct me. Like I take print screens a lot. And if I do print screen, print screen, print screen really fast, 30 frames a second, 60 frames a second, I would get, 2, 3, 5 megabyte PNGs or huge bitmaps a lot really quickly. And if I were to do that as a stream, wouldn't that turn into a movie? And how do you balance the difference between uncompressed frames and a stream?
Right. Well, that's basically the GDI way of doing it. Whereas your desktop image goes from your GPU onto system RAM when you press print screen, so that it can save to disk and all that.
Mm-hmm.
But the way that it works with the desktop duplication API is that you get a texture with DirectX, so that you can copy that texture and stay in GPU memory, and then encode it to video if you want to stream it to a mobile VR headset, or in the case of the PC VR app, just to copy it to some frame buffer and then render it. So it's very efficient because it's just a GPU memory copy. It never goes to your RAM.
Wow. When I think about texture, though, I think about when you're in a game and you look at a brick or a piece of wood and you say, wow, that's a really impressive texture. And they might be 255 or 256 by 256. I don't really think of a 1920 by 1080 texture.
Yeah, but they actually are. They are uncompressed 8-bit per channel, 1220 by 1080, or if you have a 4K monitor, it's going to be a 4K texture basically. So yes, it's a lot of memory, but it's GPU memory, so it's fairly cheap to move it around or copy it.
Interesting. Okay. And then how many frames a second are you doing this giant texture at?
It depends on your headset. If you have a Rift 90 FPS or 80, if you have the latest Valve Index, it can be up to 144 frames per second, and it barely uses any resources. It's very cheap.
That's really interesting. I think that for people who maybe watch films, they think about films as being 24 frames a second. If they play games, they think about 30 if they're old and 60 if they're a younger person. You're talking about frames per second that are really, really high, like as high as the hardware on the virtual reality device can go, right?
Right. Well, virtual reality headsets will render at a much higher frame rate because when you move your head or you move around, if you're not at a high frame rate, you're going to notice the latency a lot more than you would compared to playing a game on a monitor. So latency and frame rate are very important when it comes to VR.
Mm-hmm. And so important that it is the difference, I understand, between getting nauseous and having to sit down and having a great experience.
Right. They say that the minimum threshold is 60 FPS for VR, but I'd say it's probably more like 72, because at 60 FPS, if you look at like a white image, a lot of people will notice the flickering, the screen going on and off 60 times. Like you will notice when it's that close to your face. So Yeah, so a good, comfortable VR experience is at least 72.
Wow. Okay. Now, if you were to sit down then and figure out what it takes to push an uncompressed texture across a wire, in the case of HDMI, when you're actually tethered, you've got basically unlimited bandwidth on that HDMI cable. So there's really no concerns. When you're wired, it's not quite another monitor, but I'm sure that bandwidth isn't really an issue, right?
Right, it's in the 30 megabit, 30. Yeah, it's a lot of data, so you don't have to worry too much. The HDMI basically sends it uncompressed, full RGB.
Okay.
And when you have a wired, a tethered VR headset, yes, I capture the screen, I render it in VR, and then all that gets rendered into two ice check textures, the left and right, and that gets sent over HDMI.
Mm-hmm.
With a mobile headset, though, I send the desktop image directly, and then it's the app running in VR that then renders it in VR on the mobile headset.
Mm-hmm. Okay. So you have on the PC version, when you are tethered, the tethered version, the work is happening on the PC and the image is going across the HDMI, and you're really using the facilities of the headset to render those things, but the work's happening on the desktop, while
Yeah,
the mobile version is more client server. We'll dig into that in a little
yeah,
bit. Is that correct?
yeah. That's correct.
Okay. So I got an HTC 5 Pro, which at the time was the highest end, fanciest virtual reality headset. And they had just announced that they were going to charge you another whole bunch of money to go and get a backpack with, like, I think they called it Y-Die or some Intel fancy thing to make it
Y gig or
Y-Gig.
something
Yeah.
like that. Yeah,
Something like that. And it was basically like, we alone can solve the latency problem, and you're going to need this fancy radio frequency thing to make the wireless dream possible. Because as a virtual reality beginner / enthusiast, I've found that the tether sucks. You end up getting all tied
indeed.
up,
Yeah,
and you bump into it and you trip yourself over all the time, right?
yeah, yeah. Totally, I agree. And yeah, that Y gig standard is essentially 60 gigahertz, if I remember correctly. So it's sending a lot more data than Wi-Fi. So I think they still do image compression, but it's more like a very low latency compression. Like it's like a lossless compression where they just send the image, but they don't have much less in quality
Yeah.
over that.
They kind of narrow cast it directly to you. They only have to send it 20 feet or something, so they
Yeah.
can go really high. The thing that I think is interesting, as someone who's watched over the last 5 or 6 years the virtual reality industry change, I thought to myself, well, I guess if I ever have a lot of money, I'll buy that expensive thing, that big old backpack, and I'll put it on my machine, and I'll get that benefit. And then honestly, I got a copy of VRDesktop.net, and I don't have any of those fancy things. You're pushing it over my 5 gigahertz Wi-Fi network. What
Yeah.
happened? What technology leap occurred? I'm not saying that it's exactly technically, mathematically the same, but from the point of view of a consumer, how did you replace this expensive technology with off-the-shelf things?
Well, all our computers for the last 8 years or so have good video encoding capabilities in hardware. So that means either your processor or your video card can take a texture and then compress it into multiple textures and compress it into a video, what they call H.264 or HEVC, which are two codecs, like compression, decompression ways to compress the image. So through a codec, you can compress a video stream to something much, much smaller than the original image is. And you can compress it enough so that it fits within the bandwidth of today's Wi-Fi.
So you were saying, though, that when you're doing HDMI, it might be around 30 megabits, which
30 gigabits, sorry.
30 gigabits.
Yeah, it's crazy high.
Oh my goodness. Okay. So you are needing to get an order of magnitude less.
Yeah, yeah. It's a big, big difference.
Okay. So not being a mathematician or a particularly good programmer, but I'm just kind of sitting here in my mind doing the math here. 30 gigabits uncompressed. Now I need to get it on something reliable. We hear people about saying they have, Wi-Fi 6 or they have really nice Wi-Fi, 5 gigahertz. What's the real, true, effective bandwidth of the average Joe or Jane's wireless network?
So it depends on It depends on a lot of things. It depends on the router. It depends on the devices on both ends. So even if you have a Wi-Fi 6 router, unless your computer and your VR headset is also Wi-Fi 6, you won't be able to take advantage of the technology. So in the case of the Oculus Quest, it's a AC 802.11.AC. So that limit is, in theory, it's 866 megabit per second.
Mm-hmm.
But in reality, what you achieve is about 100 megabit per second.
Okay. So
Because
there's
it's split
lots of big
across all the
numbers on
devices.
a lot of big numbers on the box that say, yeah, you can have 800 megabits or whatever, but
Right.
the practical reality is definitely less than 100. And then,
Yeah.
of course, when you've got wood or concrete or whatever is sitting between you and the router, all of those things add up, right?
Yeah, exactly. So the 5 gigahertz signal on a Wi-Fi has a little more trouble going through walls. So if you have one wall, it might work okay. You might lose a bit of signal quality, but you can't really go like across floors and all. It doesn't work very well reliably for large amount of data. The 2.4 gigahertz band, which has much lower speeds, you can maybe do 20 megabit tops maybe on that. You will be able to go across walls and cover a better distance. So it's kind of a trade-off between distance and obstacles and the amount of data you can send.
Mm-hmm. Hey friends, I want to tell you about one of our sponsors, Text Control. They're not only the creator of the fully featured document editor library for .NET and Angular apps, but their libraries also have powerful PDF functionality. So you don't have to program PDF documents. You can make MS Word templates and then merge them with data, and that'll let you create pixel-perfect PDF and PDF/A documents. The best part is fillable form elements like text boxes and checkbox fields and drop-down elements, and you can add those easily to your PDFs and make filling out forms really simple for your users. And don't forget, TX Text Control gives developers a complete solution to handle PDF documents in any business process. So check it out. You can try it free. See the live demos at textcontrol.com/demos. Just that easy. textcontrol.com/demos. So I had this expensive HTC Vive Pro, and I was frustrated that I didn't use it often, and I was disappointed that I, spent so much money on it, and I ended up selling it on Craigslist. And I gave up on VR for a little while. And then I bought an Oculus Quest for about $300. I think they're 400 new, and used it and loved it, but realized that it was underpowered, right? You said it was a Snapdragon processor. It's basically a mobile phone in a VR headset.
Yeah, it's actually a very old Snapdragon. It's a Snapdragon 835. So those are the same processors that shipped in the Galaxy S8. And now we're like at the S20 or something. We're like 3 years later. So it's really like a 3-year-old phone processor, basically.
Okay. And so it's kind of a miracle that it's able to do what it does anyway, locally.
Yeah.
Indeed. Okay. But then I've got that big giant computer with the great video card that's just sitting here waiting to do things. And that's where VR Desktop comes in, right? You can let my computer do the work, do the rendering, and then send the frames wirelessly over there. So now you've got two apps to think about, right? We're not just capturing frames and putting them across an HDMI cable. We have a streamer app and then a mobile app. How does that architecture work?
Yeah, so the way it works is that the streamer app essentially captures either the desktop or the VR game that you're trying to play, and then encodes that into video and then sends that over Wi-Fi to the mobile app itself on device. And the mobile app decodes the video, renders it with the environment, the controls, and all that. If you're looking at the desktop, or if it's a VR game that you play, essentially it decodes both eyes, because I send an image for both eyes, and then I render those as if I had rendered them locally.
Wow. When I did it the first time, and I saw my desktop, I was like, oh, cool. Like it's a remote desktop application, and I was impressed. What I was not ready for was that I could take my Steam application, my Steam VR, and take the latest, coolest game, which was Half-Life Alyx, and play that on this tiny Snapdragon processor, because it's really just using a remote desktop kind of a vibe. I was shocked. Doesn't Steam not want you to do that? Like technically you said you kind of just said, oh, I'm just capturing the output of the game. Like, how are you doing that?
Well, actually, Valve, who are the developers of Steam, they have a driver API. So it's called, well, OpenVR. OpenVR is like a double-sided API where they have an API for games developers to develop their games on, and they also have an API for headset manufacturers to develop drivers so that it can work with any headset. So lots of Steam VR compatible headsets have their own driver. And so games can just target OpenVR, and basically that allows them to play on any OpenVR compatible headsets. So what I did is simply write an OpenVR driver for the Quest, and instead of rendering it or sending it through HDMI to a connected headset, I simply send it to the streamer app, which encodes it to video and then sends it to the mobile app on the headset.
I think that one of the things that is wonderful about having a podcast and getting to talk to smart people, and I hope that the people who are listening think this as well, is that when a really smart person who's done a really cool thing says simply twice in a paragraph while explaining the amazing thing that their application did. So you simply wrote a driver to be an open VR headset and then simply changed from wired to wireless, and it simply worked.
Yeah, it's a little more complicated than that nowadays because there's a lot of subtleties, because a lot of games were written when there was only like a Rift and the Vive, right? So a lot of games assume, oh, if it's you're using OpenVR, then you have a Vive, so I'm going to show you the Vive ones. And so when I first developed this, like, you would have a Quest, but then you would see the Vive ones and the button wouldn't match exactly. So it was like kind of an awful experience for a lot of games because they didn't correctly look at what headset you're having. So I just assumed you have a Vive. So what I ended up having to do was to rewrite the entire Oculus runtime. And then when the games are launched, I tell the game, don't use the original Oculus runtime, use mine instead. And then in mine, I pass in all the input, and then I convert the image, send it over the Wi-Fi, and stream it. So nowadays, virtual desktop is a lot more complicated because it essentially has to inject the games or Steam VR to make it think that it's actually a real Rift that's connected to the computer, even though there's none.
I will say that I was impressed that it worked, and I was impressed also that I had the HTC Vive drivers and everything still installed, and the application and Steam VR were smart enough to know which VR headset was active, and it just kind of did the right thing. So I'm really ending up using my inexpensive Oculus Quest as my primary thing. My next question is to understand the latency. You're doing all this stuff. A couple of milliseconds here and there are the difference between a great experience and nausea and being sick. How do you even start debugging those things? And what if you had found at some point that latency was introduced by one of these steps, these jumps that you're making?
So it was really a lot of trial and error until it works correctly. It might sound crazy to just do something by trial and error, but with the entire stack of having two applications, like one on the PC side, one in VR, debugging was not easy. So, and even printf debugging wasn't really an option. So it was a lot of tinkering of seeing, okay, does this help? Nope. Does this help? Nope. And then trying a lot of different things. What I can say is that the nice thing about the app is that it's developed entirely in C#. So it is a lot easier and it's all with Visual Studio, right? So I press F5 and then I can debug it. So it's a lot easier in that way because it's with a language that I'm familiar with, that I'm good with. And so Visual Studio just makes that whole experience much easier.
Wow.
I can debug both at the same time, essentially, and put breakpoints in one app and one in the other while the headset is connected via USB and all that.
So for the people who've made it this far into the podcast and have been thinking, wow, this is an amazing low-level programmer who's doing all this work in C and assembler and this and that, you wrote this in C#. How is that even possible? How are you not having, I'm just guessing here, but like Gen 2 garbage collections that freeze the whole thing and cause latency issues?
Well, I simply don't allocate. That's the trick. don't do any allocations, and that's my motto really. Since I began my career, it's very easy in C# to just say, "Oh, I'll just new that here and do that," but you have to really look at your code and really identify the parts. Okay, how can I save allocations here and avoid them on a frame by frame basis, right? So if you do something 72 times a second and you have one allocation, that means you have 72 allocations per second. That's pretty bad for the GC and for the performance of your app. So you have to be very careful. You have to profile and have to, use all the tricks in the books to optimize your code and all that.
Mm-hmm. And if you make 72 little allocations and don't clean up correctly or decide to do manual cleaning up, then you've got memory leaks. And I assume at that frame rate, you're going to find those memory leaks pretty quickly.
Right. Well, the nice part is that if you allocate managed memory, it's the garbage collector that takes care of them. I don't really allocate that much on managed memory, but if I did, yes, I'd have memory leaks. But the problem is that if the GC kicks in, not all the time, but it freezes all your threads, right? And it says, okay, I'm cleaning up, just wait a little bit. For a regular desktop or phone app, it doesn't really matter, right? You won't even notice it. But if you're in a VR app and you're doing 72 frames per second, and then you get like 1 or 2 milliseconds of garbage collection, you would totally notice it. You would sit in your headset.
Mm-hmm. Was there ever a time where you were doing this and either someone told you or you thought maybe I would not be able to finish this in C#? Like C# and the .NET ecosystem is not going to make this be possible.
Oh, not at all. I've been working with C# for 15 years, ever since it came out, really. So I was comfortable knowing that I would be able to do that entirely with the language.
That's cool. So what are the things that you can't do for App Store reasons? What are the things that, like you had said at the very beginning of this conversation, that you thought that some of these features would just be part of the headset? And when did you reach the limit of what they would allow, and when did you have to switch to side loading? And maybe explain that to folks that aren't familiar with the ecosystem.
Right. So when I started developing the mobile version that streams over Wi-Fi 3 years ago. Initially, I targeted the Oculus Go and the Gear VR, right? So to stream your desktop. There was no VR feature at the time, but the most requested feature since I released that version was, since you're connected to your computer, why can't we stream VR games? And I was always telling them, that's a good idea. I'll look into it. And so I decided to develop it. There were a couple apps, open source apps that were available that did something similar, but they were very clunky and hard to use, and they had a lot of manual steps, and connecting wasn't very easy. So I thought, I can probably do something better, something more user friendly, and so I decided to develop it for the Quest and make it work very well there. Unfortunately, I didn't have time to finish that before the app submissions were done, right? Because the Quest had like a QA period, and we had to submit our apps before the headset launched. So I didn't have time to do that. So I decided to release the VR streaming feature later on. And I was kind of bummed out when Oculus reached out to me and told me, you have to remove that feature, otherwise we're going to pull your app from the store.
And why don't they like that feature?
Well, because they were obviously themselves working on something similar. And my guess is they didn't want to be overshadowed by an independent developer working on a wireless feature. They released Oculus Link, which is a wired version of what I do. So but it's through USB. So they do the same thing where they compress the image to a video codec and then send it through USB 2 or USB 3, which has slightly higher bandwidth than Wi-Fi. And then they decompress it on the headset. So they essentially developed the same thing, but a wired version that they released, a few months later. So I'm guessing that's why they told me, it's because the quality will vary depending if the user has a good Wi-Fi and all that. I said, yeah, of course it will. It's like any PC games, right? If you have a bad computer with an old graphics card, it's going to perform poorly. So it's the same thing here. You need a good Wi-Fi, a good network, and if you have it, will perform well. So,
yeah, I went and got an Anchor brand USB-C, really high quality cable. It's like a 10-foot cable, and then I found myself back where I was again before I had the HTC Vive with a long cable, and I was tethered. Then I had the Oculus Quest with the Oculus Link Beta. And instead of streaming over HDMI, I'm streaming over USB. I'm still tethered. I'm still sitting. I just went back and started using VR desktop, and now I can walk around. I can move around my
Mm.
room. And honestly, I haven't. I know that they're telling me that there's latency, but I'm not feeling it. I'm sure that there's someone who can feel it, but I move my head and it moves. I mean, how many milliseconds or nanoseconds are we talking about here?
So in effective latency, there's about 30 seconds right now between sending the in
Milliseconds?
30 milliseconds. Yeah. So sending the movement of your head to your computer, to rendering the game, compressing to video, sending it back over Wi-Fi, decoding the video and rendering it in VR. There's between 30 and 40 milliseconds right now for most games. Depends on the game.
Mm.
Some games are take a longer time to render. But the cool thing is that I can use the features that are on the Oculus SDK, which allows me to reproject the image. That's called time warp. It's a technical term, but basically it means that I use the image that was projected for a pose, and then I kind of skew it based on the new position of the headset. So any rotational latency gets eliminated because I essentially tell the image, pretend like I rendered you at this orientation instead of this one. So you kind of get some latency gains, improvements with time warp when it comes to rotational latency.
Interesting. There's a thing in animation that you're probably familiar with called onion skinning or keyframing. So you have a keyframe where the character is in one mode, and then there's interpolating between like this motion and that motion. I move my arm from the left to the right. So you're basically, you know how they turned their head instantly. I just turned my head, and
Right.
I'm going to still ask for the frame, right? That I'm going to get back in 30 milliseconds. But while we wait, I'll just imply that you turned your head and we'll turn. And that's a
Yep,
very
exactly.
clever thing.
Yeah, that's something that's part of the Oculus SDK. So that's something advanced. Something John Carmack came up with like a few years back, and to mitigate the existing latency in headsets. So normally the headsets, when you render them, you maybe have 15, 20 milliseconds of total latency. But if you add time warp, you can kind of compensate for that latency and bring it down to something that feels like zero. So with the whole streaming part, it feels like it's zero, but there's still some noticeable latency. And for some people, they notice it more than others. It really depends on the person.
Yeah, that's a really good point. There's other little tricks. There's actually a lot of really great tricks and John Carmack tricks and everyone tricks. I was playing Vader Immortal, again, on a very underpowered machine. It was running locally on this little Snapdragon processor. And I was playing for hours before I realized that the entire viewport wasn't being rendered at full texture. It was really just a square in the middle. The peripheral vision where I wasn't looking was basically blurry. And until I decided to like look straight ahead, but think about the left and right, that's when I realized they were doing that.
Yeah, so yeah, the mobile processors are very old. So one way to do that is to kind of split the eye image that you see into different boxes and render them at full quality in the middle and then lower quality on the sides. And that's one way to save GPU horsepower on the mobile headset. I do something similar with the video when I stream. I compress the edges a little more than the center so that I use more bit rates for what's in the center of the eye versus what's around the edges. So
Which makes sense because, frankly, I think that's what God does as well with our eyes. Because I'm pretty sure that the bit rate of our peripheral vision is definitely not as high as what I'm staring at right now.
right, yeah, what's called or fovea in our eye is it can only read text or do a very precise thing straight in the middle. If you look like 20 degrees off and you try to read something on it, you can't do that at all. So our eyes work in that way. Yeah.
Very cool. So folks can check this out at vrdesktop.net. They can get it on Steam and the Oculus Rift store for the PC version, and the Oculus Go store and the Gear VR and Oculus Quest stores for the mobile versions. I can tell you that I reached out to you because I wanted you to be on the show because I am a huge fan. I love indie developers. I love seeing things in C# that are impossible. And I think that you've got a great product here, and I hope that folks check it out.
Thank you very much for having me.
This has been another episode of Hansel Minutes, and we'll see you again next week.